Good day, my wonderful viewers. You are welcome to Understanding Chemistry by Nkechi. Today's lesson we'll be looking at chemical equilibrium. So before I start, let's define what equilibrium means. A system is said to be in an equilibrium when there is no observable change in the properties of the system with respect to time. Okay, we're going to look at examples of equilibrium. So number one is a balanced seesaw. So it is the solution of sodium chloride in water until there is no further dissolution of the salt. So number three, liquid bromine in closed container with its vapor. So this number one is an example of a static equilibrium. This one is static equilibrium because it is at rest. So static equilibrium. So number two and number three is an example of a dynamic equilibrium. Dynamic. So all cases of saturated solution, because this sodium chloride, when you dissolve, everything dissolves. You put, for example, I put 5 grams of sodium chloride in 50 cm cube of water. If you put 50 grams, it dissolves. You put 10, it dissolves. You put 20 grams of salt, it dissolves. Time is when you add certain amount of salt, you will add, there will be no further dissolution again. As you add, you see some salt, the undissolved salt present in the solution. So that point, that solution is what we call saturated solution. So this one, liquid bromine in closed container with its vapor. So that dynamic equilibrium involving a physical change is called physical equilibrium. The one that involves a chemical change is called chemical equilibrium. So in physical equilibrium, there is no change in the composition of the substance. For example, look at this bromine liquid. Bromine liquid. So the vapor will rise, vapor. So evaporation of this bromine liquid will lead to bromine vapor. Whereas condensation of the vapor will also give back bromine liquid. So there's no change in the composition of bromine. Then in chemical equilibrium can only be attained only in a closed system. For example, reaction of ammonia with reaction of nitrogen. The reaction of nitrogen and hydrogen to form ammonia gas. This reaction takes place in a closed system. If it's an open system, this gas will escape, and that's the end of the reaction. But if it's a closed system, it means that this gas will not escape. What it means that this reactant will react to form products, and the product will also do what? React to form what? To give back what reactant, because they're in a closed system. When the mixture of nitrogen and hydrogen, are mixed together. Okay, when nitrogen and hydrogen are mixed together in a closed vessel, the concentration of nitrogen and hydrogen is going to decrease to a constant value. While that of the product ammonia will rise from 0 to a constant value. So at equilibrium, what happens is that the concentration of this reactant and the one of product is going to be what? It's going to be the same. So that point, we'll say that this system is at what? Dynamic equilibrium. Let's look at a graph that shows the dynamic equilibrium between nitrogen and hydrogen, which are reactants, and ammonia. The reactants being nitrogen and hydrogen, and that of the product, which is ammonia. So you can see the concentration of the reactant decreases to a constant value, while that of the product, rises from 0 to a constant. So this is the point. At this point, this is the time equilibrium is established between the reactant and the product. So this symbol represents a forward reaction. So this one presents backward reaction. So if it's a reversible reaction, it's a reaction that can proceed in both directions under suitable condition. Irreversible reaction takes place only in one direction, just like this. So this is an example of this irreversible reaction takes place in just one direction. So for dynamic equilibrium, it means that that reaction must take place in a closed system. Let's look at the properties of a system existing in a chemical equilibrium. One, a chemical equilibrium can only be attained in a closed system. So that's one. Because it's an open system, means if one of the product is gaseous state, it will escape, and that will stop the reaction. So number two, a chemical equilibrium can be approached from the point of view of either the forward or backward reaction. So three, the concentration of all the species present in a system at dynamic equilibrium remain constant as long as the reaction conditions are unchanged. So number four, a chemical equilibrium is dynamic in nature. So remember, both the forward and backward reaction go on at the same rate. A catalyst can be used to alter or change the time required to reach equilibrium. It does not affect the equilibrium position. It's just the time. So it means that when you add the catalyst, it will increase the forward and backward reaction at the same extent. So it does not affect the equilibrium position. Mass action states that at constant temperature, the rate of chemical reaction is proportional to the product of the reactant concentration. When each of the reactant concentration is raised to the power of its coefficient in a balanced equation. So look at this reaction. Let's consider this reaction. A reacting with B to give E plus G. So applying this law of mass action, this case signifies equilibrium constant. So the concentration of the product of the reactant, which is the product E, raised to the power to the coefficient E times G, raised to the power of the coefficient G, divided by concentration of A, the reactant, raised to the power of the coefficient, which is A, so 1 meter A, times the concentration of B, raised to the power of the coefficient, which is small letter b. This equation on the board. This reaction of nitrogen reacting with hydrogen to give ammonia. So we write an equilibrium constant for the reaction. So this case, this is the product, and it's raised to power 2, which is the coefficient. Then the reactant nitrogen, the coefficient is 1. So anything raised to power 1 is certain as that thing. Then hydrogen, H2, raised to the power of the coefficient, which is what? 3. Question number 1. In the reaction between hydrogen and nitrogen to give ammonia, the following equilibrium concentration were determined at 715 Kelvin. So this hydrogen is 0.52, value for nitrogen, value for ammonia. Calculate the equilibrium constant at the temperature. So I want to say that equilibrium constant is dependent on temperature, but it's constant at constant temperature. Okay, let's start. So the equation for the reaction, so I'm going to put our equation. So Kc, this is K subscript C. So concentration of the product, don't make that mistake to put the reactant. So this is square. So all over the one of reactant N2, the coefficient is 1. So you can put 1, I'll leave it at that. So hydrogen, the coefficient is 3. So there's the power, the coefficient which is 3. So I'm going to substitute that value here. The one for ammonia is 0.091. You square it. So the one for nitrogen is 1.0 times the one for hydrogen is 0.52 raised to power 3 So by the time you sum this up, square this and divide with the denominator, so the value of case is going to be, the value of case will be 5.92 times 10 raised to the power minus 2. If your lecturer wants you to put a unit for this, just to break this thing down, the unit, mole per dn cube square, mole per dn cube times mole per dn cube raised to the power 3. By the time you divide the unit, you can come with any unit for that. The equilibrium constant for this reaction, CO plus Cl2 to give COCl2 at 373 Kelvin, was found to be 4.38 times 10 raised to the power 2. So if the equilibrium concentration of CO is 0.03 and the one of Cl2 is 0.051, calculate the concentration of COCl2. So look at what I'm looking for. So put out the formula. So Kc, concentration of the product, so it's raised to the power 1. So divided by the concentration of what? CO raised to the power 1. Concentration of Cl2 raised to the power 1. So we have to make this one is out of formula. So if we make that formula, we're having a concentration of Cl2 will be this times this. Equilibrium constant times concentration of CO times concentration of Cl2. So we're going to substitute our value. Concentration of COCl2 will be, case is 4.38 times 10 raised to the power 2 times the one of CO is 0.03 times that of Cl2 is 0.051. So multiply these two together, the concentration of COCl2 will be 0.67 mole per dm cube. So this is the answer to the question. Look at this equation on the board. Nitrogen reacting with hydrogen to form ammonia. So this equation 1. So the equilibrium constant K for the equation 1. So this equation 2, you can see this is the reverse of this one. Ammonia gives nitrogen and nitrogen. So this equilibrium constant for equation 2. So this one is for equation 3. Okay, the expression for the equilibrium constant would be as follows. So let's look at the equilibrium constant expression for each of the following equations. So equation 1, of course, the product, concentration of the product raised to the power 2 divided by concentration of the nitrogen raised to the power 1, the one of hydrogen raised to the power 3. So this one is for equation 2 and this is for equation 3. So having seen this, so all this expression refer to the same chemical system and therefore must be related. Okay, let's look at the equilibrium constant for equation 1. Let's see the relationship between this equation 1 and equation 2. Of course, what we have here in equation 1, equation 2 is the reverse of it, inverse of it. So it will be 1 over equilibrium constant for K2. Okay, look at this. Equation 1 and equation 2 is related. When you reverse equation 2, it will give you equation 1. So that's what we have here. So equation 1 is inverse of what? Equation 2. Okay, let's look at the relation between equation 1 and this. Equation 1 and equation 3. Okay, look at this equation 2. Look at equation 1 and equation 3. We have nitrogen on the right hand side, hydrogen on the right hand side, and ammonia on the other side. But look at this. This one is being multiplied by a factor. When you multiply this thing by a factor, it will give you this. So when you see something like this, look at that factor. that's been used to multiply. Very important. So look at the one that has number of moles 1. So my interest will be on this one. Nitrogen that's that the mole ratio is 1. So look at this. So if I divide this by 3, if I divide this by 3, I'll be having this 1/3. If I divide this equation by 1/3, I will get this 1/3. If I divide this thing by 1/3, I will get 1 mole. If I divide this thing by 1/3, I will get 2/3. So where your eye will capture is the one that's what the mole ratio is 1, which means equation 3 is concentration of what? Equation 1. Equation 1 being divided by what? By 3. That's 1/3. Being divided by 3. Divided by 3. So this relationship, equation 3 and 1 is related by you writing that original equation. This is the original equation. This one. When you write it, you now raise it to the power of the factor, which is 1/3. That's equation 2 and equation 3. Equation 2 is obtained by reversing equation 1, and equation 3 is obtained by dividing equation 1 by 3. Simple. Let's look at question number 3. So given that the concentration equilibrium constant Kc at 500 Kelvin is 0.49 for the equilibrium reaction, this equation, the equilibrium constant is 0.49. So write an expression for and calculate the concentration equilibrium constant for the equilibrium reaction, for this equilibrium reaction. So we are asked to write the expression for this reaction and also calculate the equilibrium, calculate the concentration equilibrium, that's Kc, for this equation. So let me write the expression for this Kc. So solution. Expression for this Kc, equilibrium constant Kc, is concentration of ammonia raised to the power 2 divided by concentration of nitrogen times concentration of hydrogen raised to the power 3. So let me write the equation. Is write an expression for and calculate the concentration equilibrium constant Kc for this equilibrium reaction. So let me write the equilibrium expression for this reaction. So Kc, so it's equals to ammonia, concentration of ammonia raised to the power 8/3 divided by concentration of nitrogen raised to the power 4/3 times concentration of what? Hydrogen raised to power 4. Okay. So the relationship between this equation and this equation, let's write an expression, equation that relates two of them. What we have here and what we have here. Look at this number of mole. This one is 1. Number of mole is 1. Mole ratio is 1. What are you seeing here is 4/3. So it means that this equation, if you divide it by 4/3, you will get this. So Kc, relationship between Kc and this other Kc is the relationship. So Kc is equals to Kc, concentration of this Kc raised to the power 4/3. So that's the relationship between this Kc and this. So when you divide this equation by 4/3, you will get this. So it's like saying, oh, this equation, I raise it to the power 4/3. It's something as what? As this. So what's the value for Kc? The value for Kc is 0.49. So raise to the power 4/3. So Kc prime, we're having 0.39. So this is the answer. So anytime you're given equation like the first equation and the other one is like this, look for the one that has the number of moles is 1 in the original equation, and raise it to the power of that factor. That factor raised to power the original equation. So let's look at question number 4. A mixture of 0.50 mole SO2, 0.34 mole O2, and 0.092 mole of SO3 in a 2-liter flask was found to be present at equilibrium at a certain temperature. Calculate the concentration equilibrium constant Kc at this temperature. So this is the equation for the reaction. So we're going to look at this question. I know that yes, what we'll do in this point is to put all this concentration, write the equation for the equilibrium constant equation, and put it. Look at this thing. The value of concentration, the unit of concentration is what? In mole per dm cube or mole per liter. So this one is just mole. And in a flask, 2-liter, in a 2-liter flask. So we are going to convert this into what? To concentration, molar concentration, by finding the molar concentration of this these gases. So it means that this is mole. You are going to divide this thing by 2. Each of them divide by 2 liter to get mole per liter. All right. So let's have the equilibrium expression. So Kc is equals to SO3, the product raised to power 2, SO2 raised to power 2 times concentration of oxygen raised to power 1. So the next thing I'm going to do is to get the molar concentration of each of the reactant and product. So let's start with SO2. In mole per liter equals to mole, number of moles divided by volume. All right. So for SO2, concentration of SO2. So we are given that the mole is 0.5. So divided by the volume, which is 2. So we're having 0.25 mole per liter. So do the same for oxygen and SO3. So we're going to substitute these values into this equation. So Kc will be, so SO3 is 0.046 raised to power 2. SO2 is 0.25 raised to power 2. Then the one for oxygen is 0.17. So by the time you square this and divide by this value, by this denominator, so the value of Kc will be equal to 0.20. Thank you so much for watching. Do have a great day. The next video I'll be uploading will be on multiple equilibria. Watch out for it. Thank you. Bye.